All right, so hello everybody. Thank you for joining us today for this SEDS Online seminar. As always, we want to thank our sponsorship from IAS, which helps us to offer all of the resources that are available on sedsonline.com, as well as these online seminars. The platform online has tons of resources, so check it out. Learning tools, virtual field trips, all of those sorts of things. So make sure and take a look. Today, we are going to have a lecture by Florian Pohl, who's currently a postdoc in the Earth Sciences Department at Durham University. Florian got his PhD at Utrecht University, where he focused on the deposition of sediment by turbidity currents. Now he's bringing sort of microplastics into the game and studying how they're transported and buried by these turbidity currents. So Florian conducts physical experiments to better understand these processes, and he's aiming to sort of translate these experiments into natural systems. So today he's going to talk to us about microplastics in sedimentary systems and its role as a new particle type. And with that, Florian, I give you the mic.
Yeah, thank you very much for the introduction. And today I would like to talk about microplastics as a sediment particle and present what we know and what we don't know about these novel particle. Next slide. Okay. So, well, I'm sure you've all heard about plastic pollution, and you've probably seen plenty of those images showing litter in the environment. But despite all the plastic you see on these images, there's something else which these photographs have in common. And so most of these photographs also show sediments. And yeah, apparently plastic has become a part in many sedimentary environments. And what I think is that we as sedimentologists, we could help to better understand the problem of plastic pollution. But before I start talking about plastic as a sediment particle, I would like to give you a quick overview about the issue of plastic pollution and start there, with a few numbers on plastic waste. So since we started the mass production of plastics 65 years ago, we produced around about 8.3 billion tons of this material. And 70% of this, which is now predicted to be waste, this is 5.7 million tons. So we produce these materials, some of them as used in our households, a tiny fraction is recycled, some is incriminated, but most of it is just discarded. So we build this pile of plastic waste, which is growing and growing. And the amount of plastic waste is predicted to rise by 1 order of magnitude by 2025. This is just in 5 years. And this is the prediction of the global plastic production in million tons. And this prediction is also, it's predicted to rise. So it's the projection here. And this is due to an increased demand of plastic products, especially in developing countries, people consume more and more plastics. And if we continue this trend, by 2050, we might have produced 34 billion tons of plastics. And if we still throw 70% away, this will be 23.8 billion tons of plastic waste. So this is more than 4 times the amount of plastic waste we have nowadays. But what's actually the problem with that? Well, nowadays plastic can be found in every ecosystem on the planet. Why can I not go live? And animals will mistake these plastic with prey. So they get entangled, for example, with prey. So for example, this albatross here is feeding plastic to its baby. And then these birds have bellies full of plastic. So these bellies are blocked and then they starve to death. Or animals get entangled in plastic, like these turtles, for example, which prevent them from growing. So there's no doubt that these animals suffer from these plastic in the environments. But also smaller animals have problems with these. So these are sea animals, and some of them, for example, build these microfibers, for example, into their tissue. Or the sea cucumber here, it has eaten some of these fragments. So these animals also have problems with these plastic pollution. For some reason, I always cannot go further. And these plastics are preferred site for accumulation of organic pollutants and toxic components. So they can act like a sponge. So they will absorb toxics and pollutants from their surroundings. But there are also some additives in these plastics, like plasticizers and fire retardants, which will leach out over time. So they are not bound in the polymer structure. And some of these additives are, for example, bisphenol A or BPA. You've probably heard of that one, or some other plasticizers. And these act as endocrine disruptor, which means they interfere with your hormonal system. And they are also, it's very likely that these also cause different types of cancer. And these toxins might be passed up the food chain through these animals, but nevertheless, we also consume microplastics or plastics directly. So there was one study released or published which showed that we humans consume around about 300 plastic particles per week. But why does plastic get into the environment in the first place? So what I really like is this life cycle of plastic products. This is from the IUCN report. And it shows the production of plastic and the use of plastic and then the recycling. So usually plastic products should be within this circle. But sometimes we have this loss of microplastics to the environment out of this circle. So these are then the arrows which point outwards. And the most obvious source for plastic loss of plastics in the environment is mismanaged plastic waste. For example, here, this is a market and there's a poorly developed waste management system in place. And these people will just dump their plastic waste into this gully here. And then there's a rain or there's a storm coming, and then all this plastic will be transported away. So this is mismanaged plastic waste. But also in countries with a more sophisticated waste management system in place, we have mismanaged plastic waste. This is the city where I'm living at the moment. So this is in Bavaria, Germany. And here we have a very sophisticated waste management system in place. But what we do is we used to collect our plastic waste in these yellow bags. And every week there are then these piles of yellow bags around the city, which is ridiculous in itself. But the problem is also that birds and other animals, they know that there are food remains in these bags. So that means they will rip them open and look for food in these. And this is already mismanaged plastic waste. And it can get even worse. So when there's a storm coming, these plastic bags will fly around in the city, they rip open, and then you have the entire city trashed with plastic waste. And you cannot make sure that all of this plastic is collected. So also in countries with a more sophisticated waste management system in place, we have problems of mismanaged plastic waste. Another source is then plastic from spills from plastic production and recycling. So these are plastic beads. This is the raw material of plastic, which is then later manufactured into different plastic products. And during manufacturing, or during transport of these raw materials, there's often spilling of those. So you have, for example, beads which fall out of these bags, or you have beads which are falling out of shipping containers. And this is actually quite a huge amount of the plastic which gets into the environment. For example, this is a salt marsh area in Antwerp next to in the Netherlands. And in this salt marsh area, there's lots of these plastic beads in these sediments there, in the environment there. Another source is then during production and also during use of the products. For example, there's tire abrasion, which is apparently a huge contributor to plastics in the environment. Then there is wearing of clothes and of washing. So there was a study published that a single wash can release up to 700,000 fibers into the environment. And then we have cosmetic products where there are microplastics in, for example, these microplastics beads in toothpaste. And then there are other factors like catastrophic events. For example, monsoons can mobilize huge amounts of plastic. And then there are losses of shipping containers at sea, which also contribute to bring plastics into our environments. So where does this plastic then actually go? So what we do is we can detect, trace, and quantify different sources of these plastic pollution. And once this plastic is in the environment, it will not decompose, at least not in the classical sense. What it will do, it will break down into smaller pieces. So, and as such, plastic behaves like a sediment particle. So it's transported by wind, water, ice, and other processes. And eventually, most of the plastic will end up in the world's ocean. So it's transported through rivers towards the ocean, like much of the other terrestrially derived sediment. And there's an estimate that only in 2010, between 4.8 to 12.7 million tons of plastic have entered the ocean. So now the estimate is that between 8 to 10 million tons of plastic will enter our oceans each year. So what do we know about plastic in the ocean? So we have models that can predict the global discharge of plastic waste from rivers. So this is a model which is based on population density and mismanaged plastic waste. And with this, we can predict where plastic is entering the ocean. Then we have numerical particle tracking models where we can simulate floating plastics in the ocean. That's done here. So these plastics will be transported by surface currents, and then they accumulate in these subtropical gyres, forming these 5 big garbage patches. You probably have heard about these garbage patches. And there's now the estimation that around 5.25 trillion pieces of plastics are afloat in the world's ocean. So that's an equivalent of 240,000 tons of plastic. But there's a missing piece to this puzzle, and that's when you consider the global plastic budget. So when you calculate, or when you see how much plastic we have dumped into the oceans and how much we find floating on the surface, so when you consider the global plastic budget, you will find out that 99% of the plastic is actually missing. So we don't know where this plastic is. It's not floating at the sea surface. And even when you look at beaches and look at stranded plastics, you can reduce these number by 3 to 4%. So there's a vast majority of the plastic is just lost. We don't know where this is at the moment. So the question is now, where is this missing ocean plastic? And there are different assumptions where this plastic went. And one is, for example, it might be broken down into microplastics. Because when you measure these surface plastics, you usually use a manta trawl to sample them. And you have a mesh size in this manta trawl of 0.3 millimeters, which means particles which are smaller than 0.3 millimeter, they will just slip through this mesh. So you will not detect those particles. And it might be that they make a part of these missing ocean plastics. Some of the plastic might be in the water column. And there was actually a study published a few weeks ago, which showed that there's actually a fallout from plastic underneath one of those garbage patches. So they were sampling the water column underneath there, and they actually showed that they could find some plastic in the water column. However, it's not enough to really account for all the missing plastic. And then there's the assumption that these plastic might be located on the seafloor. So there is one study which suggests that most of the missing plastic actually is on the seafloor, which is an equivalent from then 200 million tons. And that makes sense, for example, when you look at the density of these plastics, because almost half of the plastic waste we produce has a density higher than water. So this will never float. It will immediately be sink to the bottom and is transported into sediments. And then there are other processes, secondary processes, which increase the density of these plastics. For example, biofouling and mineral participation. So this, for example, is a plastic mug, and there's some algae growing on this mug, and this will increase the net density, and then this mug will eventually start to settle to the ocean floor. So is now most of the missing plastic in marine sediments? So we still don't know this. So it might still be stored in the river sediment and never made it to the oceans. So we should also look in river sediments and see how much plastic is actually stored in our river systems. It might be stored in coastlines or in shelf sediments, or it is all transported to the deep sea. And there's a review paper which was published a few weeks ago by Peter Harris, and so it was looking at the fate of microplastics in marine sediments. And Peter Harris looked at 80 different studies reporting microplastics in sediments. And these are the different environments where these plastics were or where these samples were taken. For example, beaches, the shallow coastal areas, all the way down to the deep sea. And on the horizontal axis is then shown the microplastic concentration in these sediment samples. And apparently there is quite a large scatter of plastic concentration in these sediment samples. And I think the reason for this is that there's a lack of a detailed sedimentological assessment of these sampling locations. So they were basically sampling just somewhere on a beach without really looking at the sedimentology and where exactly they were sampling this on a beach or what type of beach it was. So I think with sedimentology, we might be able to better target possible sampling locations in particular environment. And for this, Peter Harris proposed that to a first approximation, we should assume that microplastics behave like most other sedimentary particles. But this brings then the question, at least for me, is how far can we actually use clastic sediments, especially the grain size, as an analog for plastics? And then how do plastics behave as a sediment particle? And if you want to answer those questions, first you need to look at this new sediment particle and to really understand what it actually is. So what is plastic for a new type of sediment? So plastic is used for various applications. So we use it for packaging, that's most of it, but it's also used in building construction, in electronics, in furnitures, in transport. So you name it, we have various applications where we use plastic. And yeah, we are surrounded by this material. And because of these different applications, there also exist more than 10,000 different polymer types, so different types of plastic and even more additives. However, the most common used polymers are these 7. So these are called the big 7, and they make 99% of the polymers. You will also know all these. For example, PET, you know it from your plastic bottles for your drinking water. Then there's high density PET, then there's PVC, this is the pipe under your kitchen sink. Polyethylene, these are plastic bags. So we have all these different plastic materials, and all these plastics have different material properties. Just to name a few, first there's the density. I already mentioned that 50% of the plastic waste we produce has a density larger than 1, so it will not float on water. But then there's other things like durability, rigidity, elasticity, thermal resistance. There are many different material properties. And these properties may have an impact on the behavior of plastics as a sediment particle. So we need to consider this. The next thing which you want to know when you look at a sediment particle is the grain size. And this is the same then for microplastics. So this is the classic scheme for the size of microplastic. There are some variations, but for now I'd like to stick to this scheme here. So microplastics is everything above 5 millimeter in size. And this might then break down into microplastics, and these are plastics in between 5 millimeters down to 1 micrometer. And then there are nanoplastics, which are plastics below 1 micrometer in size. And then there might be mesoplastics, which are some intermediate between macro and microplastics. And for now, I would like to focus on microplastics because these are most similar to the sediment we are looking at in sedimentology. And these microplastics might be produced by 2 different ways. So they might be primary produced. So these are raw plastic materials like these pellets I showed before, but also beads from cosmetics and sandblasting material, for example. And then there are secondary microplastics, which is the majority of microplastics, and they come from breakdown of larger plastics. And this could basically be everything. So every plastic particle can break down into smaller pieces, and then you have this huge variety of different types of secondary microplastics. And if you look at the budget of these different types of plastic, surface straws have shown that 95% of the plastic particles they were collecting were actually microplastics. And another study suggests that the mass of microplastics is 400 times the mass of the macroplastics. So the vast majority of plastics in the environment seems to be microplastics. An open question is still how many nanoplastics we have. These are still very, very difficult to detect. There's a lot of research going on to answer this question, but up to today, we don't really know that. The next thing you want to look at is the shape of these particles, and microplastics can have a huge variety of different shapes. So you can have these spheres or pellets, then you have fragments of different shapes. You can have flat fragments, flakes, films. These are them from plastic bags, fishing lines, which are kind of thick plastic fibers, and then you have these very thin microfibers, which are just a few microns in diameter. And this shape has a fundamental impact on the behavior of these particles during erosion, transport, and deposition. And in the review paper by Peter Harris, he also mentioned that in 24 out of the 61 studies on marine sediments, fibers exceeded 50% of the microplastic particles. So most particles, microplastic particles we find in the environment, they are these fibers. So this is the vast majority of them, apparently. So what do we now know about the dynamics of microplastics as a sediment? And the other question is, how do the classic theoretical calculations for sediment transport work when it comes to these microplastics? Unfortunately, there's only a handful of experimental studies published yet. So I would really urge you to go into the lab and to do experiments with plastic to really investigate this material, because we need to better understand how this actually works. But what I would like to present here now are three main parameters where there are experiments. First, it's the settling velocity of these microplastics. Then the erosion and resuspension dynamics. So what's the critical shear stress necessary to resuspend these plastics? And then one experiment where how these plastics are deposited. In this example, I will look at how these plastics are deposited by turbidity currents. So first, the settling velocity. So the settling velocity is a fundamental dynamic property of particles, and it's used for many numerical simulations. And what it basically describes is so there's a settling particle, and there are now different forces acting on this particle. So there's the gravity force pulling the particle down, and then there's the buoyancy force and the drag force, which oppose the gravity force. And then there are other parameters like the particle diameter, for example, the density of the particle, the density of the fluid viscosity. And this works all very well when we look at spherical particles. So this is really reasonably well understood, but it becomes more complex when we look at these complex shapes we find in microplastics. So depending on their shape, they have a different behavior how they settle. For example, these discs and flakes, they can tumble around or they can swing from left to right. So we have these oscillation movements. Cylinders might rotate, or they also swing from left to right. And it gets even more complicated when we look at fibers, because one and the same fiber can have different settling velocity depending on its orientation in the fluid. So when it's lying horizontal, like this fiber here, it will settle slower, but it can also be aligned vertically and then it will settle faster. And sometimes these fibers don't move, they just, so they settle, but they don't change their orientation in the fluid. But in other instances, they will move, so they rotate, for example, or they swing from left to right. So we have all these different behaviors when it comes to settling of fibers, which is quite complicated. So I would like now to show you three different experimental studies on the settling of microplastics. The first one is from Kowalski from 2016. And Kowalski, they measured different fragments of different polymers. So they measured the settling velocity there. So they use these 6 different polymers. They all have different densities, and they also have different shapes. And these are results from these experiments. On the horizontal, you have the size of these particles, and on the vertical is the settling velocity. And these points are now the measured settling velocity of these different polymers. And these lines, they are the theoretical calculation after Dietrich. And what they found is that there's generally an over-prediction of the settling velocity. So these particles actually settle slower than this theory would suggest. So another study is from Katamolino and Isachenko in 2017. And they were looking at different shapes of plastic particles and their settling velocity. So they were studying spheres, cylinders, and fishing line cuts. So these are like thicker fibers. So they have a thickness of 0.15 to 0.71 millimeters, so like thick fibers. And they did settling experiments with these different particle shapes. And there's a reasonably well fit for spheres and cylinders. So shown in this diagram again on the horizontal is the grain size, and the vertical the settling velocity. And these circles and these boxes, they indicate the experimental measurements for the settling of these spheres. And the black line is again the theoretical calculation from Dietrich. And this is a well fit. And also these dots here, this is settling for these cylinders. And there's other theoretical calculations. They account for particles which are more angular, and also they fit reasonably well for these particles. But it's more complicated when it comes to these fishing line cuts, so to these thicker fibers. So there's generally also an over-prediction of the settling velocity. So shown here, these dots, these are the different fishing line cuts, the different diameters. And with an increase of the diameter, you have also an increase of the settling velocity. So they settle faster when you increase the thickness. But surprisingly, when you increase the length of these fibers, at some point the settling velocity won't increase anymore. So you have this plateau here. And by the way, this line here, this dashed line, that's the theoretical prediction from Dietrich for the settling velocity of these particles. And what Katamolina and Isachenko now did is they developed a new approximation to describe the settling velocity of these fishing line cuts. So this is their model, this dashed line, and this is the solid line is actually the measurement, and this fits quite well these particles. So they have a way to describe at least the settling velocity of these fishing line cuts. And the third paper is from Wallschläger and Schüttrumpf that was published last year. And they were looking, or they tested different polymers, so different densities and various shapes. So they were looking at spheres and pellets, also at fibers. They also were quite thick with a thickness of 0.1 millimeters, and then also fragments. So results are shown here. So this is again the dimensionless diameter. This is the velocity, the settling velocity. And what they found is there's quite a large variation in settling velocities for these plastics. And they compared this to the study from Katamolina and Isachenko, and indeed they found this wider variation in settling velocity for all these different particle shapes. And they explain these with different polymers. So these particles have different densities and also with more complex shapes. So the shapes they used were more complex than the fragments and the cylinders and spheres Katamolina and Isachenko used in their study. But this is more realistic because what we see in nature is also a variety of different shapes when we look at these microplastic particles. The next thing they did is they compared their experimental results with theoretical calculations. So they looked at the data, so at the results from their velocity, and then made these calculations and calculated an error from the theoretical model. And they did this for these 6 studies here. And when you then look at these fibers, you see that these theoretical approximations are around about 80% off. Some are even around 800% off. When it comes to fragments, it's less dramatic, so these are around about 50% off. And then they developed a new approximation. So they modified the drag coefficient from this equation, and with this they were able to decrease this error to around about 20 to 30% for the settling velocities of these thicker fibers and these fragments. And in a follow-up experiments, they were then looking at the impact of biofilms on microplastics. So usually you have bacteria which lives on these microplastics, creating a biofilm. And when you use these particles with a biofilm, the settling velocity is decreased. So this model then no longer fits to these particles. So to summarize this, classic theoretical calculations are apparently limited to simple shapes, so to spheres and cylinders. And recent experiments improve our understanding, but more experimental work is necessary. And the main unknowns are the settling of more complex particles, which is still not done. So we don't know about the settling from disk, flakes, films, and microfibers. So these are fibers with a diameter of less than 0.1 millimeter. We don't know about the settling velocity of flexible particles, so when they start to change their shape during settling. Particles made of multiple polymers, so this is multi-layer packaging, for example, which has different densities at different locations of the particles, and then more studies on the impact of degradation and biofouling. So the next part is the transport and resuspension of microplastics and how this would work. And so one way to study the resuspension of particles is to use sediment mobility diagrams, such as the Shields diagram. And yeah, some of you might be very familiar with this type of sediment mobility diagram, but for those who are not, I would like to explain what these parameters here actually mean, because this is important when it comes to considering this for microplastics. So on the vertical axis, you have the relation from the fluid force acting on the particle to the gravity force acting on the particle. So this is illustrated here. So you have a sediment bed, and you have a moving fluid on top of this sediment bed. And then you have a particle sitting here. And there are different forces acting on this particle. First, there is the gravity force. This is pulling the particle to the sediment bed. And then there is the drag force exerted by this fluid and the lifting force from this fluid. And on the horizontal axis, you have the relation from the grain size to the boundary layer thickness. So that's illustrated in this sketch here. So here it's written viscous sublayer, but this is, let's leave it there for now. So this is let's say this, let's assume this is the boundary layer thickness. But what it basically shows is the thickness of this lower layer and the size of the particle. And if the particle is small enough to be submerged in this lower layer, then you have a lower Reynolds particle number. But if this particle is large enough, it will stick out of this viscous of this boundary layer, and then it's exposed to the main turbulent stream layer. And the idea is now, so what you do now when you do experiments for the movement of particles, this is a video of one of these experiments. So this is how this works then actually. So you have a mobile sediment bed and you have a moving fluid on top of this sediment bed. And what you do now is you increase the velocity of this fluid and you look at the point where these particles then start to move. And then you actually plot this into your diagram. So this is then the threshold of movement for these particles. And this is then at a certain velocity. And the idea is now to do this for microplastics. And there are two studies which have done this so far. And the first one is from Ballet from 2012. And Ballet looked at different plastic pellets and the movement of those. And these are plotted here. And there's a reasonably well fit. So when you look, for example, at these opaque pellets and the black pellets, they have almost the same properties, same densities and diameters. But one plots in the field of no motion, the other one plots in the field of motion. So there's only a reasonably well fit, and this is probably due to differences in the experimental approach between Ballet and Shields. But there's another thing which you should consider when looking at these microplastic. And first is Ballet only looked at spherical shapes. So these pellets are sphere, but we know that these microplastics have also complex shapes. And Ballet was not using a natural sediment bed, which means the sediment bed in the experiment was made of the very same plastic pellets. However, in nature, these microplastics are resuspended from natural sediments. So they're sitting on sand or on finer grained sediment. And that means that there are differences in size, shape, and density between the particles in the sediment bed and the particles which are resuspended. And this is very important when it comes to study microplastics, as the next study will demonstrate. So that's again a paper by Waldschläger and Schüttl from last year, and they tested different microplastic shapes and densities on natural sediment beds. So again, this is a Shields diagram where they plotted their data. So this is the Shields curve, so the threshold where these particles should move. This is a zoom in where they show the different polymers they use and the different shapes. And what they observed is that there is generally microplastic move earlier than expected. And especially this is the case for heavier and bigger microplastics. And in fact, spheres start to move the earliest. So these are the spheres they used in these experiments. And these are the first particles which start to move. And they explain this with the shape of these particles. So apparently these spheres have less contact points with the sediment bed. So that means that there's less drag force required to start to move these sediments. On the other hand, fibers exhibit relative high shear stresses. And this is surprising because you would expect that these fibers move quite easily. But apparently some of these fibers were resisting quite high shear stresses before they started moving. And they explain this with a mechanism that fibers get caught in interspaces between these sediment grains. So they are basically hauled back by these grains, or they are lying in these interspaces between some of these sand grains. And they actually also were able to see this on camera, where these fibers were really hauled in between those grains and could not be moved by the fluid. So they conclude that the drag force is more important for spherical particles, for the movement of spherical particles, whereas the lift force is more important when you look at fibrous particles, because you really need to lift them out of the sediment bed to resuspend those. And the next part, they looked at then the impact of the natural sediment bed. So what's the impact of the grain size of the sediment bed on the transport of microplastics? And for this, they tested different sediments. So they used medium sand, coarse sand, fine gravel, and also mixed sediment. Results are shown here. So each group of these columns represents a polymer type or a polymer shape. And then the color of these columns indicates the different sediments bed they used. And what they found is that a coarser sediment bed leads to a higher critical shear stress. So you need a faster moving fluid to resuspend your sediments if you have a coarse sediment bed. And they explain this with a hiding exposure effect. So that means when you have a coarse sediment bed, you have larger interspaces between these grains where these microplastics could hide, and then they are shaded from the flow. Whereas in a fine sediment bed, you have less of these spaces, which means these particles are more exposed to the flow. And this comes then down to this idea, or this particle Reynolds number, where you have the thickness of the boundary layer in relation to the particle size, which is then different for these microplastic particles on natural sediment beds of different grain sizes. And this hiding exposure effect was actually developed in the 80s. There's the equation by Wilcock, and Wilcock introduced a hiding exposure coefficient to this equation. And Waldschläger and Schüffroth used this now to explain or to describe the movement of the plastic particles in their experiments. And then they developed these approximation here to describe this. So to summarize this, the Shields parameter may provide a good first approximation for microplastic transport, but there is an additional complexity due to the shape of these microplastics. So we should consider the differences between drag and lifting forces. So different particle shapes react different to, or require different drag or lifting forces for their movement. And then particles also may lie on the sediment bed at different orientations. When you, for example, think about microplastic films, they might lie flat on this sediment bed, and then they are shaded from the flow, or they stand upright and they're easily picked up by relatively slow moving current. This is also something which impacts the resuspension dynamics of microplastics. The bed roughness, so the particle Reynolds number, may differ for microplastics because these microplastics are resuspended from natural sediments and not from other microplastics. So there are differences in size, shape, and density between the particles in the sediment bed and the particles which is resuspended. And this comes then back to the hiding and exposure effect, which Waldschläger and Schüffroth explained. And further, not yet investigated factors are, for example, the behavior of microfibers, so fibers really with a lower diameter, only of a few microns, and microplastic films, flexible particles which can move, then again multi-layer polymers, how they would behave, and also the impact of degradation and biofoaming. So finally, the deposition of microplastics, in this case, the deposition by turbidity currents. And these are experiments I've conducted myself in Utrecht University. So then we had these 4 meter long elongated flume tank, and we fill this flume tank with water. And then we have a mixing tank where we can generate a mixture of sediment and water. So this is 450 liter of initial mixture then. And there we added traces of microplastic fragments, in this case, the melamine fragments and polyester fibers. And these are real microfibers, so they have a diameter of 12.5 micron only. And this mixture is then pumped into this flume tank and then released through this impact inlet box, and then it will flow through this flume tank driven by its excess density. So that's a video of one of these experiments, one of these turbidity currents. It travels roughly with a meter per second. And during the experiment, we were siphoning these flow at different elevations above the bed. So with these siphon samples, we were first able to look at the concentration of sediment, which is in suspension. So we look at the how much sediment is actually in the water there at this location, and we can plot this in this diagram. So on the horizontal, you have the sediment concentration per volume, and on the vertical, you have the height above the bed. And these dots indicate now these 4 siphon tubes here. And this is a typical sediment concentration profile for a turbidity current with an increase in sediment concentration towards the bed of the flow. But the next thing we did is we took these samples and we separated the microplastics, which we put in before, from these sediment samples. And we compared the concentration of these microplastics in the sediment with the initial concentration we had in the mixing tank. And this is shown in this diagram here. And what we first showed is that turbidity currents are efficient in transporting and bypassing microplastics, so they can funnel these plastics down. And what we also see is that these fibers are less stratified than fragments. So fibers are shown here in red, fragments are these bluish colored circles. And these fragments are more stratified, so you have a higher concentration towards the base of the floor, whereas the fibers are more homogeneously stratified. And this makes sense when you think about these microfibers, so they're easy to keep aloft and easy to get in suspension. And next thing is we looked at the deposits. So after an experiment, you have deposits in your flume tank, and we sampled those deposits and looked for the microplastics, or if there are any microplastics in these deposits actually. And what we were expecting were quite low concentrations of fibers, because they are lighter, easy to keep in suspension, and they were less abundant at the flow base. So we assumed that there are almost no fibers in these sediment beds. But apparently we found the opposite. So these deposits are enriched in microplastic fibers. Apparently, or actually we found higher concentrations in the deposits, in the sediments from the deposits, than we found in the sediments in the mixing tank. And we explain this with a special deposition mechanism for turbidity currents, where these fibers are removed from suspension by settling sand grains. So there's kind of a rain of sediment grains during deposition, and this will hit individual fibers and pushes them down into the sediment bed. And some fibers may then also be trapped partly before they are buried completely. And this is quite comparable with the experiments by Waldschläger and Schüttrumpf, where they also explained the higher critical shear stress necessary to move these fibers with a mechanism where these fibers are trapped or caught in the interspace between the sand grains. So these are two mechanisms which are quite similar. So to summarize this, the dynamic properties of microplastics. So the dynamic properties are essential to predict microplastic movements and distribution of microplastics, especially for numerical modeling studies. Experimental work suggests that these dynamics differ from that of natural sediments. In particular, complex shapes of microplastic, they yield some rather unexpected results. So there's deviation from theoretical calculations, especially when it comes to settling velocity of microplastics or to the critical shear stress required to move them. And for these studies, therefore, these new experimentally derived approximations should be considered. And there's more fundamental experimental work necessary. So we need to understand how these films and microfibers behave as a sediment particle. We need to know how flexible particles react and mixtures of different microplastics, because usually in nature we don't find an individual plastic, we find mixtures of different types of plastics. Then particles made of multiple polymers, like these multilayer packaging. The impact of degradation and biofouling, how will this impact the behavior of these sediments? And then the interaction with natural sediments, not only the interaction of fibers with sand grains, what was already shown in these experiments, also the interaction with clay, for example. So it seems that some of these fibers might stick clay together and result in these clumping effects. So nevertheless, these plastics are present in every sedimentary system on Earth. We can find them everywhere. And much of the missing plastic is probably stored in sediments. And therefore, I think sedimentology might be a very strong tool to detect part of these missing plastics. So we should definitely address this issue and look for plastics in sediments. And as a first approximation, these classic theories for sediment transport should also be used to detect microplastic hotspots in the environment. So we should use our knowledge on sediment transport and make predictions where we would expect these plastics to be. So we should definitely do that, but we need to be aware of the limitations of these predictions, especially when it comes to settling velocity and critical shear stress. And I think there's more fundamental experimental work necessary to fully understand the complex dynamics of these microplastics. But nevertheless, microplastics may also provide a change or a chance to improve our understanding of sediment transport dynamics. So you can see these microplastics also as a tracer, or you can prove your theory with these microplastics, depending on how it behaves. You can test whether your theory is right or not. Yeah, that's all I have to say for now. So thank you very much for your attention. And I also would like to thank my co-workers and co-authors who worked with me over the last couple of years. So thank you very much. What do I do now?
Chelsea will be with you in a second. She was muted.
Okay.
Chelsea, you should be able to unmute now.
Okay. So
Yeah,
quick break for me, but thank you, Florian, so much for the wonderful talk. I surely enjoyed it, and it's super interesting. I think as sedimentologists, we all have one more dynamic to look at, definitely within some of our sediments and our sampling. So everybody, you can start typing your questions for Florian into the chat. Please remember to send them to everybody, not privately. And when you ask your question, let us know where you're joining in from. So while we wait, maybe I can snag one question before everybody else pops in there. So you started to answer where my train of thought was going at that last slide, but sort of as sedimentologists, where are some of the hot spots that we should be looking at? I mean, obviously there's not quite enough information yet, it sounds like, but can you give some ideas that might help people that work in certain environments to start thinking about this?
Yeah. Can you see this slide now?
Yeah.
So you should look then at this review paper by Peter Harris, where he really summarized really nicely where you can find different concentrations of microplastics, so in which different environments. And it's in these low energy environments, for example, in lagoons, which you just mentioned, you found this high concentration of plastics in lagoons, but also in fjords. So in these systems close to the source, apparently there seems to be high concentration of these microplastics. So
just generally, as far as we recognize right now, sort of the low energy systems are going to provide.
There seems to be a correlation with these fine-grained materials, but it's not completely clear if this really is the case.
Okay.
Many of these studies don't even report grain size, so sedimentology is really, many of these studies don't consider that so much.
Sure. All right, so let's get to some of the questions from people joining in. We have Meg from Durham that says, thanks for a great talk, Florian. Do you know if there have been any studies showing these microplastics flocculating and behaving in a cohesive manner?
Flocculating microplastics, I'm not aware of a study which shows flocculating microplastics. So what happens is you have fecal pellets of microplastics. So animals eat microplastics and they have these pellets, but this is something else than flocculation of plastics. What we also saw in these experiments when we started to use these fibers, when you put too much fibers into this liquid, they also will start to flocculate. So they will build these small clumps of fibers. So this is also something which happens there, but only at very high concentrations. So I think you would need quite high concentration of microplastic fibers, but then this could be possible. If how they interact with clay is not really clear to my knowledge.
Okay, our next question is from Val, coming from Oslo. Excellent talk, Florian, very interesting. Quick question, in your flume experiment, did you see a proximal to distal separation of the particles?
Actually, we didn't check that. So I don't know that. So do I have these? No. So we didn't look at that. So I can't tell.
Yeah. Interesting idea, maybe for the
also
future.
the thing is I try to there it is. Yeah, the thing is also you have these siphon tubes here. Can you see that?
Mm-hmm.
And the deposits behind these siphon tubes, they're disturbed by these siphon tubes. So you could actually only look at the deposits which are here in the front of the siphon tubes. So there were only 3 centimeters of deposit we could look at. And that's the thing. So if we sample those deposits, we don't know if the turbulence of the siphon tube has disturbed those.
Yeah,
that's why we just didn't look at them.
Makes sense.
So I would love to do other follow-up experiments with these plastics, also in a bigger flume, in a 3D flume, to really see the distribution of these particles. Also, I have no other types of microfibers which I would like to look at. And then then also more complex particles like films and plates.
Sure. Yeah.
Where they end up.
Yeah, there's, I'm sure, a ton of variety of different aspects that you could throw into the game.
Yeah.
Okay, our next question is from Gary, joining from Imperial College. He says, thanks for a really interesting talk. Do you have a sense of how differently pristine and weathered plastic particles may behave?
Yeah, when you look at this study from, where's this? Here. So this is from Waldschläger and Schütthoff, this paper. And so they were looking at not really weathered microplastics, but at least microplastic with a biofilm. And these were settling slower. So apparently there's more roughness to these particles. But how they compare when you look at the critical shear stress, for example, I'm not sure. Might be that they're picked up earlier because they have a rougher surface, but maybe they also have more contact points with the sediment and they're transported later. So yeah. Not sure.
Some good ideas for future experiments, I think. Okay, so our next question is from JP Trabuco. He says, hi, Florian, interesting. The idea that marine organisms and birds somehow see plastic for food made me think about fecal pelletization as an important particle size changing process. Do you think this might make transport of, oh dear.
Yeah. Hi, Joao. Yes, this is definitely a factor which is changing the size of these particles and which also contributes to settling of these particles in the first place. So sometimes these particles have lower densities and floating, then animals eat them, then there are these fecal pellets, and then they sink to the bottom. Mm-hmm. And so at the end you have these clusters also of different microplastics in these fecal pellets. And it might be also that they are then on the ocean floor, and then they change again, and then these fecal pellets will release these plastics again, and they will rise up again to the surface. So it might also that there's a down flux, but also an up flux from the sea surface due to the fecal pellets.
Just an idea. Okay, our next question is from Maurice Tucker. Hi, Maurice. He says, very interesting, Florian, but I wonder how you identify the smallest particles as microplastics. What techniques do you use to determine the percent in the sediment?
What you do there is you take a particular weight of sediment, like 50 grams, and then you separate with a heavy density with these microplastics, and you basically count them. So the numbers given is particles per grams of sediment, so particles per mass. So, and this can go down that you have 50 grams of sediment or even more, and you count a single plastic particles in these sediments. So this is what you can actually find also in some of these natural environments.
Mhm.
Like here, some studies which have they have 2 particles. This is per kilo even, so this is even more, and these have like 6 particles, and others go up to more than 3,000 particles per kilogram of sediment.
Yeah, so if you're using a general density of sediment, what type of sediments are you using then to sort of distinguish?
Quartz sediment, yeah.
Okay,
Oh,
yeah,
what you
I
mean
guess that might create a lot of variability between different sediment types, right? Just to
yeah. So there's no sediment which actually has this low density. So there is no direct analog sediment for this type of particle. So I have a paper here where you have these.
So moving on, we have, of course, many comments saying very interesting talk, very nice, thank you very much.
Some technical difficulties. I could not change the slides.
Oh, that's okay. That's okay, no problem. We can just move on to our next questions. You can leave it there for now. So Aldiar from Moscow says, thanks, great talk. What would be your first place to take the sediment samples from? And is there any sampling program?
I think there are several sampling programs. If I can take any sediment sample from anywhere.
I'm not sure exactly what his question is, but maybe he's thinking in terms of one hotspot, where would be,
we're expecting most of
where would your ideal sampling location be for microplastics?
You mean where I find most microplastics?
Sure.
When I want to look at most microplastic, I would probably look at these quiet environments like these lagoons, fjords, and then it also depends on the input of plastics in these systems. Yeah. But the sample I really would like to have is a sample from a natural turbidity current. So a sediment sample from one of these turbidity currents where I can actually see if there's plastic in suspension in one of those flows. Yes. So that would be. So I would like to have a sample from a flow actually, and then of course also from the sediment deposited by this flow.
Mm-hmm. Okay, so Gloria is joining us from Spain, soon Colombia, and she says, great work and presentation, Florian. I'm so excited about all of this, as it can have many links to sedimentology. One idea, knowing that we have a lot still to understand and do in terms of microplastics research, should we form a diverse international group and come up with a project to the current UN Decade of Ocean Science calls regarding ocean actions? And she says she is in if anybody else is interested.
I think it would be great to make these bigger projects and to join forces to do research here. But it's also the question what we can actually achieve with this type of research. So because we basically still try to understand the problem with this research, so we will not save or we will not solve the problem of plastic pollution with this. So we can better understand where this plastic will go, where it will end up, what harm it will do eventually on the seafloor or somewhere else. But we also need to raise efforts in really preventing pollution of plastic. So really to prevent these unnecessary usage of plastic, this increase of waste of plastic. So I think these are real important points when you really want to tackle this problem of this pollution, because these cleanup projects, like when we identify now hotspots on the ocean floor, like contorite deposit, drift deposits, where we found apparently quite high concentration. These are these points down here. Mm-hmm. We cannot go down there and clean these contorite deposits from microplastics. This is just impossible, and the environmental impact of such a cleaning operation would also be massive. So we cannot remove these plastics from the environment. We can basically just study them and look where they are, and if they create much harm. Yep, definitely.
And maybe homogenization between different research groups and how to measure them, all of those sorts of things. So she did add the link there. So if anybody's interested, you can chat together in the chat room, and you can also discuss at any of the coffee breaks via SEDS Online. So, all right, we're going to move on to the next question. We have Jason saying, apologies if this question is slightly off the main topic, but could the missing microplastics be accounted also in the groundwaters, which are not present in the surface and sedimentary systems?
In the groundwater, so some of the terrestrial plastics.
Mm-hmm.
So these missing plastics, they refer basically or mainly to the marine plastics. So this is the budget when you estimate how much plastics is dumped into the oceans and how much do we find in surface waters and on beaches, for example. So missing terrestrial plastics, I'm not aware of that.
So Jason, maybe something for you to look into, terrestrial plastics.
Yeah, definitely. There's also terrestrial plastics, and you have plastic in soils. So there's I know groups who are working on plastic in soils for farming, for example, where they find these microplastics also. There's airborne microplastics. I haven't even touched this subject, but we find them in snow, in the Arctics, in mountains, on top of mountains. So we can find them everywhere. So airborne plastics. So there's no environment safe from microplastics. Question is just what are the concentrations are. So if is a lot of plastic or just minor fractions, which might be not a very big issue for the ecosystem if there's only a little bit of plastic.
Okay, so our last comment for now, and keep typing them if you have them, everybody, but is from Niels, which says, thank you for the sum up of recent investigations. It's just a comment, I suppose. We have conducted a large-scale experiment in waves in the large wave flume in Hanover, Germany, and implemented microplastics. We also identified buried particles all over the depth of the mobilized sediment along the flume. Yeah. So I guess sort of an add-on to one of your comments about within the sediment, actually, not just in the inside of the flume.
Yeah, it's not just on the top. This is also within the sediments.
So Niels, if you have a paper or a DOI for a paper, then you can place that in the chat and everybody can have access to it. Unless we have any more questions. Okay, we have one from, okay, the paper is under revision, so keep us updated and we can retweet you and everybody can get access that way. One more question from Lawrence in Dublin says, great talk. Are electrostatic forces important for deposition of fibers?
I think these might play a role when it also comes to clay particles, and that might not be only limited to fibers. So it might also with other particles, but it more depends then on the polymer type of these plastics. But it might be that this plays a role. The question is if what are you looking at when you look at the turbidity current, where you have really these massive forces, fluid forces in the flow, and you have some plastic fragments, so the majority is just plastic sediments. Then there's the question if these electrostatic forces between these plastic and some of these particles play a big role in how these particles will behave as a sediment. So might be that this exists and that this plays a role, but difficult to quantify. Yeah,
I think it sounds like I mean it's a pretty fascinating area of research, and it sounds like there's a lot to be done along with all of the great work that's been accomplished so far. But yeah, so we're excited to hear more development of this issue. And
I hope, yeah.
Yeah. So if nobody else has any questions, well, we will thank you again, Florian, for the wonderful seminar today, and remind everybody that next week we have our seminar again at the normal time, 4 p.m. British Standard Time, where we'll hear from Michael Strasser about extreme events in the geological record. And thank you. See you next week.